My name is Hendrik Heuer and this is my talk titled Hacking Human Language. You might wonder why it's called Hacking Human Language. It's a very pretentious title and I know that, but I really love the hacker ethics. And the hacker ethics says that access to computers and anything which might teach you something about the way the world works should be unlimited and total, and also to always yield to the hands-on imperative. So the idea is to learn through doing, which I really like and which I embrace in my studies as well. So the agenda for the talk is to talk a bit about computational social science, to talk about natural language processing, word vector representations, and I'm going to compare different Wikipedia article revisions, talk a bit about random indexing, which is another way of doing word vector representations, and then I'm also addressing the word2vec patent. Quickly about me, I'm a happy European, I'm a German living in Sweden, studying at a Finnish university in this wonderful European Institute of Innovation and Technology, and I'm doing my master's thesis on natural language processing and machine learning. So quickly about computational social science, which is also sometimes called digital humanities, especially here in Oxford. And the idea is basically to combine computer science with social science. And this makes new research possible. For instance, you can analyze massive social networks, and you can also analyze millions of books. And if you look at the graph down here, then this is actually all my emails. So it's 27,574 mails and 222 people analyzed. And as you can see, the green ones are my friends from university in Bremen, the orange ones are my friends in Stockholm, and the blue ones my family. And you can also get the names of the people, but I removed it for this. Another really nice research piece of research I like is this one. And of course, this is just a map of Europe. But interesting is how it came about, because this just comes from the data. So people took the Flickr data with the GPS coordinates and then just plotted the GPS coordinates. And as you can see, if you do that with tens of millions of Flickr photos, the European map emerges. But not only that, if you then look at the text of the images, you also get a really good city guide. You get the Eye of London, you get the Cathedral of Cologne, and I found that was pretty amazing. It just goes what we can do. And you can apply these computational means to journalism. So there's a paper called Massive Scale Automated Analysis of News Content, where they took 2.5 million articles from almost 500 English language news outlets and then automatically annotated that into 15 different topic areas, and then looked at readability, linguistic subjectivity, and gender imbalances in regards to these topics. And it's quite interesting. So if you look at linguistic subjectivity, that's basically just looking at the adjectives in the sentences using a technique called part-of-speech tagging, and I'm going to show you how to replicate that and do that yourself. And then they have this database, the CentiWordNet it's called, which basically says that humor is a positive word or like hate is a negative word. So you take all the adjectives and then you look up the sentiment of the word, and then you look at different topics. And it turns out that fashion is much more linguistic subjective than politics, elections, and business. And the hypothesis they now have based on this data is that the low level of political interest and engagement could be connected to this lack of subjectivity, because it's also a bit more boring to read if there are no adjectives. Another interesting thing is looking at the female to male ratio. So they use a technique called named entity recognition, where they just find first names and then they have a list again of male and female names. And this is pretty crazy. And the nice thing about this is, like, people might have this intuition that there's not enough reporting about women in sports, but now you can quantify it and you can actually make it very, very obvious. Because if you do this, you see that in sports, only 7 to 25% of the coverage is about females. And that's pretty crazy considering that there are 50% females in the world. So this is what you can do with it. And for me, it is a bit like playing Lego, because you're just connecting these ready-made blocks. So you can do text processing with NLTK, with word2vec, with spaCy, and I'm going to talk a bit how to use that. Then you can visualize it with different JavaScript libraries, which is nice because then you can put it on the internet. You can do topic modeling with gensim, and you can do machine learning with the wonderful scikit-learn. So if you were to replicate the results I was talking about, you could use NLTK and then you can do this part of speech tagging, and you might remember that from school. It's just these are the nouns, these are the verbs, these are the adjectives, and as you can see, it's more or less just one line of Python or 2 lines where you tokenize the words, and then you do the part of speech tagging. Similarly easy is the named entity recognition, where you can see that it can actually recognize New York City as a geopolitical entity, and this you can also use to get the names. And then another thing you might be using, which might be quite helpful, is this technology called sentiment analysis, where you want to tell if a sentence is positive or negative. And again, if you actually do what they did in the paper, and that's just looking at single words, then you won't be able to classify a sentence like this, because the sentence reads, "This film doesn't care about cleverness, wit, or any other kind of intelligent humor." And as you see, the single words are quite positive, but the sentence is not. So to do this, you can use a recurrent neural network, which was what Roloff was talking about today. And actually this is implemented in Java, but I think this is the best. And you can just integrate it via a subprocess if you want to use it. But the main thing I wanted to talk about today is word vector representations. And it touches a bit about the previous talk, but I hope it's not too redundant. So the main idea here is that words are represented by their context. So this is the famous quote by Firth, the linguist, who says, "You shall know a word by the company it keeps." And what this basically means is that if you take a word like banking in the middle, then the words surrounding it in the usage represent its meaning. And that's one of the most successful ideas of modern statistical natural language processing, and it also enables us to represent words with vectors. And as you remember from school, hopefully, vectors are just directions in space, right? So the goal is to find just a bunch of numbers in these directions that represent a word like linguistics. And in doing so, you actually encode relationships between the words. So the vector going from men to women is very similar to the vector going from uncle to aunt, or from king to queen. So you can just basically just take this, it's just a direction in space, and you attach it to king, and you end up almost where queen is, because you do a nearest neighbor search in the vector space. And this holds true for plural. So there's also a vector going from king to queens, which is similar to king to kings. And for capital cities, so you can take the vector going from Paris, from France to Paris, and attach that to Spain, and then you end up in Madrid. So as we already saw in the other talk, we can do these analogy puzzles, which are closely connected to intelligence tests. So you can say England is to London as Germany is to Berlin, or more high level, England is to Cameron as Germany is to Merkel. And this also works for more linguistic things. So you have the superlative, you also have the past particle encoded, and you can do it also with more obscure things. So I played with it a bit. So if I put in Scotland and haggis, then I get the currywurst in Germany. And I'm very happy it's not the sauerkraut, because currywurst is much nicer. And then I told my brother that I snuck in currywurst into my presentation, but then he said, you should also do Marx if you can do currywurst. So I have communism and Karl Marx. And as you can see, and of course Karl Marx is not literally communism, but if you do that with capitalism, then you have Friedman, Keynes and Hayek. And I think it's pretty cool how much it can capture just from the distribution. You can also look at the most similar words. So if I put Sweden in, I actually get the Nordic countries. And this makes a lot of sense, because if I have a lot of sentences, just imagine some sentences like Sweden is a country with a lot of trees. Then you can find also a lot of sentences saying Norway is a country with a lot of trees. So these are actually quite replaceable in their usage in the language. You can also do it with Harvard, and then you get Yale, Cambridge. So now I'm going to show you how to do that in Python. And it's very, very easy, because we have these wonderful libraries we can use. So in gensim, you have the models.word2vec, and they are just implementing this paper from Google titled Efficient Estimation of Word Representations in Vector Spaces. There's also another library which you can use, which is called spaCy, and that's implementing a different model. Because I will show you how the word2vec is working. This is a similar model, but this takes the sentence structure into account. So if a word is a noun or if it's a subject, then that makes a difference. So here is an example of how these word embeddings look like. And again, it's just the words from the context. So if you have the 2-word context window, you look at turning into banking crisis as, and then try to predict a vector for the word banking. You can also do it with a bigger context window, or you can then use it also with this part of speech tags, and like this is a subject, this is the adverb. And if you do this, you end up with quite different representations. So if you do it with Florida, for instance, if you do the context window of 5 with word to vec, you end up with cities in the state of Florida. Whereas if you do it with the dependency, like this is the subject of the sentence, then you end up with other US states. And even cooler, if you do it with Hogwarts from the Harry Potter universe, you end up with, in the simple word to vec example, you end up with Dumbledore, with Malfoy and Snape. And in the dependency case, which you have through spaCy, you have other famous schools from fictional schools like Sunnydale from the Buffy the Vampire Slayer universe. So if you were to use this, it might be helpful to train it on your own data. And fortunately, this is very easy. There's a nice generator which is very memory friendly, and I took this right off the gensim documentation, so you can use it quite easily on your own data. It just takes a lot of time to train them if you have a lot of data, obviously. If you don't want to do that, you can also get pre-trained vectors from Google. So they trained their vectors on 100 billion words, and they provide 1.4 million pre-trained entity vectors. But why would you do that? Why is this even interesting? So one nice and obvious application of this is machine translation, because it turns out, and again, these vectors just emerge from the usage of the words, and as you can imagine, the word dog is used similarly in Spanish as it is in English. So you basically just take the vector for dog in English and look at the numbers representing it, and then you take that into the vector space which you trained with Spanish words, and there you end up with the Spanish word for dogs. You have to do a bit more, like the paper goes into detail on how to align it, but basically it actually works. So how am I using it? I'm using it to compare Wikipedia revisions. So I do these 3 steps. So I find the word representation for a word, I do dimensionality reduction, and then I visualize it. And as I already said, I use gensim to find this word representation, and again, it's very, very easy. So this is the code I'm using, this is the actual code, and this is the important part of that code. So you basically just load the word vectors, and then you go through all the words you have, and then I'm actually keeping track of the words because I only need the word vector once, even if a word occurs more than once. And I'm also kicking out the too frequent words because they're not that interesting to me. And then if the word is in my model, I'm just collecting it. So again, this is just what I want. A high dimensional vector. This makes it look a bit more low dimensional than it is. It is a 300 dimensional vector, but you shouldn't worry too much about it because we're actually scaling it down to 2D anyways, so that we can plot it nicely like this. And we're doing this with TSNE, the T-distributed stochastic neighborhood embedding, which you don't really have to implement yourself because we're lucky and we're using Python, so we can just use the scikit-learn implementation. And it's, again, just 2 lines or 1 line if you really want to write it as 1 line, you can do so. So you say, we want 2-dimensional vectors. I'm fixing the random state to be able to compare my results, and then you do the fit transform where you give in the word vectors and you get out 2-dimensional vectors, and then you can use D3.js to visualize it. So this is how it looks like. And just to give you a bit more of an intuition, so I put in the Wikipedia article on Game of Thrones, and then I have these regions of similar words, because similar words are encoded similarly. So as you can see, this has to do with TV series and characters and themes and fan fiction. You can also get the bird's eye view, and that's zooming out. And now you can compare different text sources, because you might see, and I'm sorry, but this is very small, but that's not the point of it. You have the orange and the red ones. So the orange ones are the 2013 revision of the Wikipedia article on Game of Thrones, and the other ones, the red ones, are the 2015 ones. And the white one is the intersection set. And as you can see, if I toggle this a bit, then it is actually quite consistent. But some words get added, and that's where it gets interesting, because there is this section in this larger map that has the character names. And as you can see, there are some character names removed, and there are also a bunch of character names added. So this is a really nice way to compare text sources from the top, and I'm using this to compare books with book summaries to make sure that the right topics are covered in my master thesis work. You can also do it with one of your former colonies, the United States, and as you can see, that one didn't change that much. And yeah, but some words were added and some words were removed. Then there's one thing I actually wanted to talk about as well, because while I was preparing, there was a lot of outrage on the internet because there was a patent. And the patent is on the name of Mikolov, who is also the one writing the paper. And I followed the discussion on Reddit, and it's quite interesting. So there are a lot of different viewpoints, and so many people said it's just Google protecting themselves against patent trolls. Others thought it was not enough for a patent and said they might as well just patent matrix algebra. Others don't like the idea of patents altogether. And there is a nice post by Omer Levy, who was the author of the other paper, which takes the dependency of the sentence into account. And he also said that the novelty claim is somewhat bogus, and that Word2Vec is just doing what the NLP community has been doing for 25 years, but very efficiently with very good pre-processing hacks and nice hyperparameter settings. So it's just a brilliantly efficient implementation. So yeah, but the main, and then there were people saying, but wasn't it released under Apache license? And that's exactly what Thomas Mikolov then replied on the mailing list. He said, as far as he knows, it is under Apache 2 license, which means we can use it as much as we like, and that it's just a protection against patent trolls. And there is another good indicator that this might actually be the case, because Google has been doing this with Hadoop as well. So they have a patent on it with MapReduce, but you can of course use Hadoop. So let's hope for the best. There's another similar idea called random indexing, so basically Word2Vec is trained with a neural network, whereas this is just vector math. So random indexing is another incremental word space model where all information is encoded in vectors. So for each word you have a hash key, which is just an n-dimensional vector, and n can be 1,800. And then for a very small number of these 1,800 dimensions, you set minus 1 or plus 1 values, right? So this is kind of how it looks like, although there are much more zeros. And then so the dimensions of the vector is much, much smaller than the number of contexts. And you have this hash key representing a single word, and then every time you see a word used in a context of another word, you add the words in the context vector to the context vector of the word, which is pretty much the same I was just showing you, right? You see banking and you see debt co-occurring, so you add debt to the vector, the hash key representing debt to the context vector of banking. And then if you do that often enough, after a number of occurrences, this context vector does hold information about the word's distribution. So this is a form of dimensionality reduction, and the advantage is that these vectors it's just this one vector which has all the information. So you can, for instance, just take the information from the Twitter firehose in real time, because you're not training and you're not dealing with a neural network per se. And this is what GoverGuy is using and doing, which is the company of my professor. They're not only taking the Twitter firehose, but also blogs and all kinds of other real-time sources, and they provide this living lexicon. So for instance, last week there was this nice news that the Philae lender woke up again. So at that day I looked into how what words Philae is associated with. So you can see comet, ellipse, Rosetta, Osiris, the comet trajectory. So you have this dictionary which is learning from the current data. And this is quite interesting, because you can also look at other words like Athens, for instance. And if you look into Wikipedia for Athens, you see the Hellenic Parliament, you see the Acropolis as words associated to Athens. But if you actually look at the discussions online, it's much different. People talk about Grexit, people talk about the Eurozone, and renegotiations is one of the words that comes up. So this is quite interesting because you can learn a lot of things about the words and its usage. But what about more than words? Where can we go from here? Because this is quite simple after all. The most obvious thing is, of course, not only to represent words with vectors, but also to represent sentences with vectors and to represent documents with vectors. And luckily and happily enough, you can actually already do this in gensim. There's another model which you can use so you can learn vector representation for sentences. And now it gets really interesting because people also use this to do image captioning. So you use some of the fancy models Roelof introduced, and you're basically combining these word representations with a convolutional network, and then you end up with a system that you train with a bunch of descriptions and a bunch of pictures, so like in pairs of course, so an image with its description, and it learns to represent them similarly. And if you do that long enough, you are in a nice situation where you just put in the image and get back the description. And that's literally making the blind see, which is pretty awesome. And of course it has a lot of nice applications for a company like Google's. And as you can see, this works quite well. So you have the black and white dog jumping over the bar, and you have the surfer on the wave or the girl in the pink dress. And even if it is slightly off, it's still pretty cool. So if you look at this, this is a man in black shirt playing guitar, it says here. The guy is tuning the guitar, but it understood a lot about the picture already. Here it says 2 young girls are playing with Lego toys. Of course, this is not a young girl, it's more like a mother or sister. And what's really cool in this particular case, it actually got the backflip, but it didn't get the trampoline and thought it was a wakeboard, which I think is an honest mistake. So as you remember, we have these vectors encoding relationships as well. So you can actually do this with the images as was shown. So you can take a picture of the Taj Mahal, you subtract the word day, you add the word night, and then you have buildings at night. It's not quite the Taj Mahal, but it's still pretty amazing. Or you do a picture of a car in blue, you remove the vector for blue, you add the vector for red, and you end up with red cars. So this is research from 2014, and like some weeks ago there was another even more exciting paper where you do image question answering. So you ask what is there in yellow in the picture in the middle, and it can reply banana. And this is super exciting, and I'm really curious where this will be going. But it's also the end of my presentation, so thank you for your attention. And you find the slides here on the website if you want to check them out, or email me if you have questions. Of course, you can ask them now as well. I didn't use so the question was what did I use for clustering? I didn't use clustering per se. I was taking these word vectors and I was using TSNE to project them down. And it's a probability. It's basically looking at the probability distribution in the high dimensional space and the one in the low dimensional space, and make sure that they're similar. So words that are similar in the high dimensional space are similar in the low dimensional space. And then these clusters are just emerging. So that's like the clue of my summarization, right? Yeah.
Sorry, this is all really new to me and really, really interesting. So I'm afraid this is a really stupid.
Oh, no worries. That's awesome.
Answer it anyway. Ask it anyway. I would, as you're showing it on the diagrams, the vectors are sort of inverse. The vector from king to queen is the sort of the same but the opposite direction as the vector from queen to king.
Yeah.
Whereas I would think, in fact, the vector from queen to king, if you're starting with queen, should be different, because as you're going from, if you get queen minus woman plus man, you might get prince. I mean, if you look at this country, we have prince rather than king. So you've got a slightly different vector going on, because sometimes queen minus woman plus man will be king, and sometimes queen minus woman plus man will be prince.
Yeah, I think you should much rather think about it in terms of encoding certain relationships. So you have this one encoding the gender, and you have this other one encoding the plural, the gender, or like the royalty, like vector. So I hope this, like, are you Rolf? I don't know.
Yeah, I'll get you.
It's algebra in short. Yeah, it's algebra with vectors. The vectors have meaning. And,
yeah, it just.
I just wonder that you might, depending on your start point for the vectors, whether you would end up with a different vector if you were focusing on queen as the start point versus king as the start point, and whether it would be interesting to see which concepts have different relationships to each other depending on which one you're starting with.
yeah, you can do that. I mean, you can start from any point to another point, and that's the direction you map.
Yeah.
And then you can say, well, now I have this direction, right? And then take another vector, and then I say, well, now I want to encode the same direction back to what should be the origin point for this vector.
And
No matter which, there is no, actual geographical, logical way to go about it.
it's all about the relative relationships. There's no global truth to it, right? Like it's like they can be like colors can be close to cities or something, right? But the cities will be close to each other, the city names, and the color names will be close to each other. Yeah. Any more questions? So yeah, thanks a lot, and have a good day.